in addition to the bit flip code, we also looked at a phase flip code. And let's just look at it very briefly here. We're not going to go through the same analysis, but I want to show you the parallel of what the syndrome measurement operators are. Here, the logical code words were plus, 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 and minus, minus, minus. Remember, plus and minus are 0, plus and minus 1, divide by root 2. OK, and here, the syndrome operators are easy to figure out directly from the bit flip code, because remember, all we did to get to the phase flip code was to apply a Hadamard operator. So if we apply a Hadamard to a Z operator here, so we conjugate H, what do we get? X. That's right. So U1 will be XXI, and U2 will be IXX. And this is because HZ, H is equal to X. And so in the Hadamard basis, we say the syndrome operators become these XXI and IXX. OK, so that was very fast. Now, the reason this is useful to go into is because it lets us revisit this famous code, Shor's 9-qubit code. The problem with the bit flip code here is that it only corrects for bit flips. This only corrects for phase flips. And you'd like to be able to correct for an arbitrary single qubit error, which is what the classical codes do. They correct for arbitrary single bit errors. But here we have to correct both phase and bit value errors. And Shor's 9-qubit code was the very first to ever do that. And when he came out with it, it was beautiful and obvious why it worked, but people didn't have a theory of why it worked and what it is a member of a family for. And I'll get a little into that when we see the conditions for quantum error correction. But now that we have this formalism of what the syndrome operators are and the recovery operators are, we can easily see what the 9-qubit code is doing. So remember, the code parameters are n, k, and for this, n is equal to 9, and k is equal to 1. OK? So the code words of the Shor code are these. 0 is 0, 0, 0 plus 1, 1, 1. Tensored 3 times, normalized by square root of 8. And logical 1 is 0, 0, 0 minus 1, 1, 1. Tensored 3 times divided by 8, square root. Now what I want to give you is the syndrome operators for Shor's 9-qubit code, because that way you'll know what the entire error correction procedure is. You can figure out what the recovery operators are fairly straightforwardly. But the syndrome operators might not be so obvious. They are Z1, Z2, Z2, Z3, Z4, Z5, Z5, Z6, Z7, Z8, Z8, Z9. And these correct for what kind of errors? Yes, please. Bit flip errors. And then perhaps the non-obvious ones are the phase flip syndrome operators. They are x1, x2, x3, x4, x5, x6. So that's one operator. And the other one is x4, x5, x6, x7, x8, x9. So altogether we have 1, 2, 4, 6, 7, 8 operators. It encodes 1 qubit. And this is not an accident that there's always seems to be one fewer syndrome operator than the number of qubits that are used to do the encoding. Okay, so we had a 3-qubit code here. We have 2 syndrome operators. We have a 9-qubit code here. We have 8 syndrome operators. And there's a pattern to this. And that pattern we will not see in this semester's course, but it led to a beautiful PhD thesis from Caltech by Daniel Gottesman, which set the floor for something today known as stabilizer codes. And that's a beautiful formalism that is almost directly analogous to the formalism of linear codes for classical codes. And we don't have the time to cover that this semester, but it's a beautiful theory that you can get into if you take the second semester course. Okay. What I want to do, though, is to take 5 minutes or so and just challenge you to give me an error, and then we'll work out the syndrome for that error for the 9-qubit code. I claim that every single qubit error you give me, that's an x, a z, or a y, because y is x times z with up to signs, there will be a unique value of the 8 syndrome bits that we measure here. Okay, and we don't have to work them all out, but at least one of those syndrome bits should be a 1 instead of a 0, showing me that there's an error associated with that syndrome. Okay, so somebody give me an error specified by an x, y, or a z on a specified qubit 1 through 9. Who's first? You've raised your hand too many times. Anybody else? This is an easy question. Yes, please.
X on 5.
Yes, x on 5. So let's write a little table for an error which is x on 5 in this case. Which syndrome operator is non-zero? Okay. So I claim that that's covered right here. This pair of z's is actually measuring the parity between qubits. So it says, are these 2 qubits the same? Are they both zeros or are they both ones? If they're both zeros, then this is a 0. If one is a 0 and the other one is a 1, then the measurement gives you a 1 instead, because it sees the parity is different. Notice how it's always comparing 2 qubits. It never looks at the value of the encoded qubit. It looks at these patterns between qubits. So if you flip just the 5th qubit, then this suddenly will give you a minus sign, and this will give you a minus sign. So we get that Z4, Z5, and Z5, Z6 will be non-zero. Now, if you flip a qubit like the 5th qubit, does that change the value of this syndrome? We didn't go into the phase flip code very much, but there should be a fast way by which you can argue it does not change this syndrome measurement value. Why is that? And it's just the idea that this error commutes with a measurement observable. And if you commute with a measurement observable, you don't change the measurement result. So x5 commutes with this because it's just another x. And so it doesn't change the measurement result. But the reason that's true is exactly the one that you described. So it's more fundamental to say what you said. And the upshot is that we can use this simpler argument of any observable that commutes with your measurement observable cannot change the measurement value when you're making these larger arguments. Okay, so another error. That was an easy one. Y6, right, great. Okay, so Y6 is a product of Z6 and X6. So you can think that both errors occurred. Now that X6 is clearly going to change this operator here and not this operator. So we get a Z5, Z6. But the X6 is going to commute with all of these. On the other hand, the Y6, the Z6 is going to commute with all of these. Remember, these two are the phase flip error syndrome. And so the Z6 is going to trigger the X1, X2, X3, X4, X5, X6 operator, and that's going to be equal to 1 when you do the measurement. I'm missing one too, right? It's also going to trigger the last one. So that's X4, X5, X6, X7, X8, X9. So in many ways, what you can do is you can think this combination here of the first 3 qubits is actually like one Munster qubit. And here's another Munster qubit. So this is like X1, 2, 3, X4, 5, 6 is equal to this thing. And this is like X4, 5, 6, X7, 8, 9 is equal to this thing. So you can see this is just like the bit flip cases here, but with a Munster grouping of 3 qubits acting as 1. And the reason that's true is because we have this structure up here of a plus, plus, plus. If I were to write out that whole state, this 0, 0, 0, plus 1, 1, 1 cubed, see, I started dropping my cats. This is 0, 0, 0, plus 1, 1, 1, 0, 0, 0, plus 1, 1, 1, 0, 0, 0, plus 1, 1, 1, like that. And so this is, if you look at it from afar, it looks like a Munster plus, plus, plus. And then the 0, 0, 0, minus 1, 1, 1 is something like a minus, minus, minus. And so that's the phase flip code. That's why our error syndromes look like these groupings of X's together. Okay. So this is a game that you can play. And what you'd like to do is to figure out the minimum number of these kinds of syndrome operators in order to be able to uniquely determine a given error. And this gives you bounds on how many qubits you need in order to correct what number of errors and so forth. And so that gets very interesting.